Welcome to Maths with EJD. I'm making a series of videos on basic calculus. The last set of videos were on the applications of integration. So in this set of videos, I'll be talking about integration, and it's quite elaborate indeed. So let's see what we have to face here. Of course, this is the fifth module of this, and it is about integration. So I'll be making up to 10 videos because it is quite extensive. So talking about integration, these are the things we'll be considering. So I'm going to make a video on basic principles of integration, followed by integration of polynomial functions, then indefinite and definite integrals, integration of derivative function ratios, integration of trigonometric functions, integration by substitution. I'll make one video on algebraic substitution and then another on trigonometric substitution. That's 7, right? Integration by parts will be 8. Integration of compound fractions will be 9. And then I'll show you some basic formulas and several practice questions. That'll be the 10th video. So let's go on this jolly ride. So we talk about basic principles of integration for starters. And let's see what the whole idea is about. So if you must know, the integration and differentiation and integration, they are like two sides of a coin. While differentiation is like breaking things down or tearing things apart, integration is gathering things together or building things up. So in another sense, integration is like you're removing things. It's more like division, separation or division, right? And integration is about summing things together, So technically, integration is adding things up, while differentiation is breaking things down. All right. So talking about the basic principles of integration, we can first of all see integration as anti-differentiation. Or is that word anti now? Anyhow, you think it is. I think I at least call it anti-differentiation. So given the function y equals 4x squared plus 5x plus 7, we already know from the idea of differentiation how this should go. It's a polynomial expression, so the differentiation is relatively simple. So from our knowledge of differentiation, we proceed as follows. We say dy dx is d dx of 4x squared plus 5x plus 7. Being a polynomial function, we know 4x squared is just going to be 8x, and 5x, when we differentiate, will be 5. 7, when we differentiate, will be 0 because it's constant. Now, we are talking about integration, right? But integration can be seen as anti-differentiation. So now we have differentiated that function. What we want to do now, you want to integrate the result. The result of that is 8x plus 5. So let's integrate that and see what happens. So if we turn around to integrate, though the general concept has not been introduced, we have this. I've not talked about integration in general, but I mean, this is us going ahead of ourselves just to make a point that integration is anti-differentiation. So, what you got last, if you remember, is actually that dy dx is 8x plus 5. So if you multiply both sides by dx, you're going to get dy equals 8x plus 5 dx. And that is exactly what we have brought to this place. So dy is 8x plus 5 dx. So to integrate now, you just put the integral sign. This is actually it's if you can see look at it like I told you, the integration is also summation, right? You can look at it like summation stretched out. So this is summation for discrete variables, discrete countable variables. But this is summation for continuous variables. Variables like discrete variables is some things you can count, like 1, 2, 3, 4, 5, that you can count separately. But continuous variables will be functions like maybe you want to integrate from maybe 1.5 to 1.7. That's like you can't really hold down 1.6, 1.7, like it's a whole stretch. So that's why this summation for continuous function, while this is the normal summation, for discrete expressions, discrete variables rather. Okay. So dy dx is 8x plus 5 dx. Then you put the integral sign on both sides to integrate. And so you can now break this apart. So this is more like 8x plus 5. And the principle of integration, as you're soon going to find out, is this, that when you have 8x raised to power 1, to integrate, add 1 to that power and divide by the new power, which is 1 plus 1, 1 plus 1. So because 8x has power 1, so that's 8x squared divided by 2. Then for 5, right, you can see 5 as like I said during differentiation, you can see 5 as 5x raised to power 0. To integrate that, add 1 to the 0 and divide by the new power, which is 0 plus 1. So that's why you have 5x raised to power 1 divided by 1. So that's how to integrate. So now you discover that if you integrate 8x plus 5, you get 8x squared divided by 2 plus 5x raised to power 1 over 1, which means you have 2 here, 1, 2 here, 4, and then you have 4x squared plus 5. So that means y, you see that y now is 4x squared plus 5x. Now, but the trouble with this is what we actually started with 4x squared plus 5x plus 7. So now the 7 is missing. And that is also something important to talk about. So it's like I've got the original expression back, except that 7 is missing. So from the result, we see that we have a function looking almost like the initial function, which is y equals 4x squared plus 5x plus 7. So it is obvious that integration is a process of anti-differentiation. So the reason for the 7, we are going to find out now, that is where the idea of arbitrary constant comes in. So from the first expression, right, we discover that the 7 in the initial function is missing. That is from what we call equation 1 here, this one, that y equals 4x squared plus 5x. Okay, you discover the 7 is missing. So each time differentiation is done, every constant value goes to 0. So when you have when we differentiated 7 initially, it went to 0. So as a result of that, whenever we integrate, an arbitrary constant is added to the result to compensate for any likely missing constant. Okay, so because the 7 is constant, we don't, but when you integrate, you do not even know whatever that constant was initially. So as such, for dy dx equals 8x plus 5 dx, a more comprehensive result would be y equals 4x squared plus 5x plus c, because there might have been a constant, and the constant could even be 0, it could be 7, it could be minus 7, it could be anything, but we don't know. So we just add c, or sometimes you can add k depending on what the situation, where c is the arbitrary constant. In order to get the actual constant, more information will be required. So, I mean, generally, this is what you have when you integrate. But, I mean, if you have extra information, it's very possible to get the arbitrary constant back, precisely, but that will require extra information. And that's what you have in this last line, which says, for instance, given dy dx equals 8x plus 5, and you now have this extra information that y of 0 is 7. Y of 0 equals 7 means that when x is equal to 0, y is equal to 7. So that's like an extra information that can help you in getting the arbitrary constant c, which we added here initially. So, and if you do that, right, you have y equals 4x squared plus 5x plus c. So, and you've heard now that when x is 0, y is 7. That means you have 7, y now is 7 equals 4x squared. 0 squared is 0. 4 times 0 is 0. 5 times 0 is also 0, then plus c. So now you see c is equal to 7. So it means that instead of just having y equals 4x squared plus 5x plus c, then you can now finally have, so you obtain your c to be 7, just like we have here, and then we would have y equals 4x squared plus 5x plus 7 as given initially. But if you don't have that that extra information, you just leave it with the arbitrary constant c, like explained earlier. Okay, so that's the idea. So lastly on that is you should know that integration can also, like I've even said it before, that integration is summation too. You can see integration as summation over for a continuous variable. So integration can be regarded as a process of adding things up, that is a summation. So whenever we wish to find areas, under curves, volumes, etc., we can do this by finding the area or volume of a small portion and then summing over the whole region of interest. The calculation can then be performed using the technique of definite integration. So I've told you already that integration can be seen as summation. So as integration as a sum can then be expressed as what you have here. So the integral of f of x dx between a and b can be the same thing as the limit as delta x tends to 0 for the summation of f of x delta x from x equals a to b. So it's more like as you sum a function over a long towards infinity, right? It results to this integration. So generally speaking, in summary, this whole video is about the fact that integration can be seen as the opposite of differentiation, such that whatever you differentiate, by the time you integrate it to get back to the original function, then integration can also be seen as a summation. So if you have not subscribed to this channel, make sure you do that and click on the notification bell so you can always get the other videos that will come. Thank you so much. In the next video, we'll be talking about integration of polynomial functions. Of course, after all the videos, the 10th video will be, I'll show you several examples that you can try your hands on. So be sure to look out for that video where you can see so many questions and even general formulas for integration that can come in handy for you whenever you need them. See you in the next video.